right, welcome. Obviously, if you're watching this, you're watching the video because no one else is here. It's a little bit early. It's going to be business as usual to claim the points for this video. Pay attention. Occasionally, I'm going to say an attendance word or an attendance phrase, or it might even be a question. But anyway, you're going to write those down. You're also going to take a screenshot every time I say one of those attendance words or phrases, or whatever it may be. And at the end of it, when it's all done, going to send me an email that has all the attendance words and phrases and all the screenshots for every time I said one of the words or phrases. You have to have both to get any credit. And just as a heads up, the last, word for attendance or phrase for attendance is I'm going to ask you to write one question about the material presented in this lecture. So as you're watching the lecture, if there's something that makes sense to you or you just wanted to clarify something, just go ahead and jot it down. That way, when you send me the email, that can be your last portion of the email. So that's it. So it's about 7:30 here at the moment. So that means you can go ahead and skip this video ahead about 30 minutes, and then you can then the lecture will start. So then I'm just going to be doing some work and watching some other stuff on YouTube. Hmm. Morning.
Y'all just think we can fill our grade shoes?
You think, you can try it.
I put the grade in, and I don't know if that bothers you, but
No, it doesn't bother me. I'm just
I think it's 9.
make sure that it all matches up and then sign it.
I also appreciated it. One day. You and me make some.
How about this? I won't do it this time.
Oh, yeah, I'm not gonna do this.
No, I'm gonna say that if you email me, all right, I'll email you if I remember.
Okay,
Tell you which name you missed.
yeah.
If you watch the video or send the words.
Okay, yeah, I can do that.
Where we at here? Yes, I don't do it. It's not good. The opportunity to fix it. Yeah. Such a hassle with this thing. Like when you go run this year grade, like you said, it'll give you your grade.
Yeah.
All it gives me is points. So, I mean, I
That's,
gotta-
you know, Dr. Manny?
Oh, yeah, I had him as a student once.
Yeah, he integrates for me, that's all I can see. My end, it's just
Interesting.
like I just wrote down what I have in the exam, just my grade. All of my class. He hasn't corrected this single step.
Oh, wow.
In 6 weeks.
Well, I mean, I haven't either, but
But that's different.
yeah, it's a
Like my
extra credit for us.
history of psychology. That's the only discussion.
Oh.
Graded was 6 weeks.
It's crazy. Yeah, it's a B. This,
It was in 88, and then I put this one, it was 9.
yeah, well,
The only thing I'm gonna question about is my C's.
you can just leave it as an A. Man, my biology teacher in high school was an Olympic high diver, a gold medalist, and every lecture she had had something to do with that. So I didn't pay any attention. I hated biology in high school.
Yeah. I was not going to do that. Science.
All right, that's good. Yeah, I was bad at chemistry too. Well, I didn't even take chemistry until I got to college. I almost changed my major. That was my first semester. And I've been out of college for like a decade. Real chemistry's up at basically algebra. And I was like, I don't remember, 'cause I hadn't had algebra for 10 years. So I failed to pass with a C. But then got A's after that. That first semester was tough.
My roommate last year, so before I got here, 92 guys over been here for baseball, and he was, I don't know what his major was, his minor was right. He had a bunch of chemistry classes. He took consumer chem last year, dropped his minor within 2
Wow.
weeks of starting that class. He had to take like 6 or 7 chem classes.
Yeah. Also, the guy who taught me wasn't, his teaching style and my learning style didn't mesh. Let's put it that way.
I didn't, like, I'm weird. I got really good at chemistry, because I do find it interesting. I'm just not good at math. But I figured out how to do chemistry and math, like for basic chemistry. Like our class average was exam last year.
Damn.
The one exam, there's 2 people above 50, it was me and another guy. Bruce, we had Bruce right in classes. He's super smart.
What's his last name?
I don't know his last name. I don't even know his name because he's in senior center. 7 people. Because he got a 97, I got a 91.
Nice.
And like the baseball players I sat with, one of them was way better in school than I was. Like,
Shoo.
yeah.
That is rough.
Yeah. Like when we started balancing equations and stuff, we don't take our time on that.
Yeah, that is a challenge. That's why I like organic chemistry. Everybody complains about organic chemistry because it's not math. It's like you have a drawing of a molecule,
Yeah.
a drawing of another molecule, and you explain how this one attacks this one, and like what the atoms are doing while that's happening. It's not lovely.
In consumer can the organic chemistry that far it was like drawing them. But we had a cheat sheet to draw everything. So I don't know how people struggle with it sometimes.
If you got a cheat sheet, it's
Yeah.
a lot easier.
And like our professor explained it very similar to what he explained with drawing. It's like all you really have to do is figure out how many times you're saying
That's basically it. Oh, so you guys didn't even have to do 3-dimensional drawings? You just did it like you did in our lab? Oh, even easier. 3-dimensional is where it gets a little bit harder.
I think the only issues with Prometheus, it wasn't for organic, but like for H2O. And
Had to have the bend, yeah. Did they explain why it has the bend? Like the lone pair is pushing down? Yeah. Well, that's good.
That's like the Lewis dot diagram here were a little weird for me. We got so in the habit of drawing the electron left over.
Yeah.
I know you wanted to do something like that, so I ended up redrawing it. I think
Oh, man.
the first three, I think I kept the electrons. And I was like,
Oh, that's no big deal. Mostly I say that because like if I have a student who's that just sucks at like they're just horrible at everything, and now all of a sudden they've got these perfect Lewis dot structures, and I'm like, okay, clearly you looked that up. I mean, not clearly, but it's a good indication that they didn't do the work. That's all that is. I have a lot of rules like that where I don't necessarily enforce them, but they're there. That way, if I need to. But like I did a lot of my online students. They drew a lot of them with the OH like right next to each other,
Yeah.
which is common. But that's not how I taught them. So I'm like, I can tell you looked it up. It's, but anyway. morning. And should probably go to the doctor. Sick for over a week now. Yeah. Okay. In less than a minute, I'll go ahead and get started. And Brian Bell's here. My champion's here. How you doing? Dorby, not here. Gross, not here. Gunther is here. Hill, is here. Yep, Randall's not here. You're here. Jackson? Here. Is here. All right. Keys is here. Perez is not here yet. Sigmund is here. Slaughter, not here. Smith is here. Stover's here. Tompkins is here. Van Nest is not here yet. Watson is not here yet. Young is not here yet. Zweiback is here. Lawrence, not here yet. Carter is here. 8 o'clock, I'll wait till 8:01, see if anybody else shows up between now and then. So I didn't miss anybody, right? Everybody's making a call. All right. All right, 8:01, we'll get started. Attendance, again, mandatory, graded. You guys know the procedures. Even if you're watching the video, you know the procedures too, because I said it when I started recording earlier. Missed it, go back to the beginning of the video and read the procedures. But anyway, yeah, attendance is mandatory, graded. The first word for attendance today is homecoming, because it is homecoming. Speaking of which, and I know I've asked this before, but I'll ask it again for the sake of everybody else. What time is the game and who are we playing?
1:30.
1:30? Fairmont. The other FSU, the one that's going to lose this weekend. The other FSU is going to win tonight against Virginia. Anyway, that's great. So let's talk about that very quickly.
Not too much on my state.
Virginia's going down. Anyway, pre-lap 6 is due today, right? You guys should have already received some sort of reminders for that. make sure you get it done today. We go ahead and skip ahead. I'm in office hours until noon, so if you need my help, ask me for help. I'm happy to help you. Again, you don't have to do these pre-labs by yourself. They're not quizzes. I'm here to help you and teach you. If you were absent from lab on Wednesday, remember all you had to do was be there and you get 20 points. If you weren't there, then you have to watch the video that's already posted, and then you have to do the virtual lab to make up for it. It's not fair to your classmates that you could get 20 points just by not showing up, but they also get 20 points. So if you have any questions about that, see me after class, and I'll help you with that. But yes, everything you need is already posted to the course announcements. The lab, the free lab, video, PowerPoints, the form that you're going to use for your lab report. It's all there. Any questions about the lab that's coming up that we've been working on? All right. So I got some good feedback, and I wanted to bring it up. Speaking of labs, yes, you are responsible for all the data, right? You guys put the data on the board. You only do one experiment, but you're responsible for all the data. So if someone screws up, it's up to you to talk to those people. It's up to you to use some critical thinking and look for red flags. Like, that doesn't look right. Now, some of you might think that's a bit too picky, especially when it comes to grades. But I wouldn't do that if I didn't allow you to fix your grades, right? So I allow you to fix your grades. Therefore, it's not a big deal, right? So, for example, the table from last time we did an experiment that said that there was no water left in the beaker because the cell had sucked it up. A lot of people lost points for that. First of all, it's only 1 point, so that's probably not even going to change your letter grade for the exam or for the lab, even if you didn't fix it. And second of all, again, you can go back and fix it. So I wouldn't be so picky if it wasn't for the fact that I do let you go back and fix it. So thank you for the feedback for the person who told me that. And I just wanted to let you know that's the method behind the madness. It's all on purpose, right? It's to get you thinking critically and seeing red flags in data. So any questions about labs? All right, so again, like I mentioned previously, the office hours today are until noon as usual. But unlike usual, but I don't plan to work this weekend. So go ahead and look at anything you might need to look at and let me know if you need help because I might not be available this weekend. You can try to reach me this weekend. Call my office phone. It's forwarded to my cell phone, but most likely I won't be available. Any questions about that? All right, another thing I noticed when I was perusing the WVSU online, I noticed that some of you have done those the discussions. So I'll remind you again, the discussions are extra credit. And because of that, because I've got so much other stuff going on, I haven't even looked at your discussions yet. So when I get a chance, I'll go in and give you feedback. Because that's the purpose of the discussions, right? Because you present something that you think is true. And my idea, I'm there to let you know if you've messed up. That way, not with the grades, but just so you can learn what you're supposed to learn. So I'll take a look at those eventually. The extra credit isn't going to get kicked in until the end of the semester anyway, so it's not affecting your grade. But just want to let you know if you've done some of those discussions and haven't heard back from me, I apologize, but that's why. So any questions about discussions? All right, finally this one too, and you guys should do this. You guys can retake the exam, because the people who you didn't know you could retake it are still talking. They're probably not hearing me. But you can retake the exam as many times as you want, and then let me know when you're done. Keep taking it, keep taking it, keep taking it. And then you have to email me and say, I'm done with it, I'm ready for you to change my grade, because I won't know until you tell me. And then afterwards, when you can no longer retake it, I can meet you online. I'll give you all the correct answers, because you're going to need that to study for the final exam. And you get a 5% boost to your grade, to that exam grade. So any questions about any of this? All right, does anybody else have any announcements or reminders or anything like that? Okay, let's jump into it. To remind you, big picture here, this next exam, exam 2, it's almost entirely about energy. And that may even be a test question too, because I keep saying it, right? This whole, remember we talked about all the different properties of life. This next one is all about energy. And for example, the one after that, number 3, for the most part, it's going to be all about reproduction, which is one of those properties of life. So yes, most of what we're talking about in this is energy. First, we talked about kind of like why your cells need energy, right? We talked about enzymes and active transport and stuff like that. Then we went in to talk about how your cells make energy, so to speak. Remember, energy can't be created or destroyed. But remember from last chapter, we talked about how cells break down glucose to make ATP, because your cells need ATP, that's where we get our energy. Now, we're kind of backing it up a little bit and figuring out how do we get ATP, or how do we get the glucose to make the ATP, and that's what photosynthesis is. So we're still doing the overview. Prior to today, I gave you a little bit of background information. Today, I'm going to give you a little bit more background information. Hopefully today we can actually start getting into the nitty gritty, but we'll see. See what kind of time constraints we have. So again, this is just an overview. We're going to go over the overview and then we'll go back and look at the details. But just so you know, just as a reminder, when it comes to the questions about respiration, which is the stuff we just finished, most of the questions are going to be, in which stage does this happen? In which stage does that happen? In which stage is this produced? In which stage is that used, right? That's going to be most of the questions. Same thing for photosynthesis. So as I'm going through this, keep that in mind. That most of the questions about photosynthesis are going to be, in which stage is this used? In which stage is that used? In which stage is this produced? In which stage is that produced? So that, keep that in mind. That's what most of the questions are going to be. Also keep this in mind. I think this is the first time I've told you this. For the exam, when you get those types of questions, what stage does this happen? What stage does that happen? If it says, for example, in which stage of photosynthesis is oxygen produced? And I'll give you that answer here soon. You're going to have, it's a multiple choice question, right? So two of the choices are going to be light reactions or Calvin cycle. And then you're going to have a bunch of garbage from respiration. As long as you guess light reactions or Calvin cycle, you're going to get at least partial credit. It's the first time I'm telling you this. The only way you can get 0 credit for any questions about photosynthesis is if your answer has something to do with respiration, and vice versa. If you're answering a question about respiration and it says light reactions, then you're going to get that 0 credit. But at least if you say, pick one of the ones from respiration, you should get at least partial credit. So anyway, let's talk about this now. So photosynthesis, again, it happens in 2 stages, unlike respiration, but it has 3. In a sense, photosynthesis is the opposite of respiration, and you'll see how as we get started. So let's start this overview. The first stage is light reactions. Light reaction uses chlorophyll. So I've already told you what chlorophyll was. We talked about that on Wednesday, right? Chlorophyll, that's the pigment. That's the stuff that absorbs energy. And actually, we're going to go talk a little bit more about chlorophyll later today. We're going to get more information about it. We'll dig a little bit deeper. But this is the stuff that converts the chemical energy of ATP, converts the sunlight energy to the chemical energy of ATP. And look at this. A new term I haven't taught you yet, but let's see. You can guess what it is based on what I've told you before. And I said there's going to be a third one that you've never seen before, but based on what that molecule looks like, you should be able to tell me what it does. What does that thing do? Because it's all something very similar, 2 very similar ones in respiration. And I said, you don't even know the difference between these things, but when you see something that looks like that, you should think, oh yeah, this is the thing that. Somebody? All right, how about extra credit for somebody who guesses it correctly? No, still. All right, carries electrons. Remember, you had FADH2 and NADH in respiration. Now you got this thing called NADPH, right? Doesn't it? It looks very similar. When you see anything like that on the exam, whether it's photosynthesis or respiration, you should think, oh yeah, that's the thing that's carrying electrons. Anyway, so again, we're talking about light reactions. Again, this is what uses the light energy of the sun to convert it to the chemical energy of ATP and then NADPH. This is also where the water is used, because water provides the electrons and produces oxygen. And again, this is just an overview, so I'm going to come back to this minutes later, a few slides, and we're going to talk about it in more detail. But yeah, so remember when I said photosynthesis is like the opposite of respiration? That's another great example. Remember, in respiration, glucose provides the high energy electrons. It gets accepted by oxygen, and that forms water. In this case, it's the opposite. Water is providing the electrons that eventually get incorporated into glucose. But when the water provides those electrons, it produces oxygen. So again, it's the complete opposite of respiration. And before I move forward to talk about this second one, I'll give you some test questions that are going to be on here. Which of the 2 reactions uses chlorophyll? Light reactions. And that should be easy to remember because remember, chlorophyll is a pigment. Pigment is something that absorbs light. So obviously that would go with the light reaction. Which of the 2 stages produces ATP and high energy electrons, or NADPH? Light reactions. Which of the 2 stages uses water? Light reactions. Which of the 2 stages produces oxygen? Light reactions. And there's another way I can help you remember this, and I'm going to probably say it a few times in this lecture. But light reaction produces ATP and high energy electrons. Here's how you can think about it. I should have said this before we started. Big picture here. The whole idea of photosynthesis is to make glucose, right? So in a sense, you can think of this as a factory. In the Calvin cycle, which is what we're about to talk about, that's the thing that's actually producing the glucose. But just like any other factory, you need materials and you need power, right? You need power to make these things. And that's what the light reactions provide. So light reactions are powering the factory, which is the Calvin cycle. So if you can remember that, that'll help you remember that the light reactions must be the one producing the ATP, right? Because we need energy to build glucose, and Calvin cycle is where we're building the glucose. So obviously, Calvin cycle is the one using the ATP. If we're building glucose, we need to incorporate those high energy electrons that we kept talking about from respiration, right? We kept saying stripping away high energy electrons. We need high energy electrons to come from somewhere so we can incorporate it into the glucose. Well, that comes from the light reactions, right? So when you think of light reactions, and light is a type of energy, you should think about energy. Producing energy, not using it, right? Light reactions are producing the energy that the Calvin cycle is going to use. So any questions for now about light reactions? And again, we're going to come back and talk about it in more detail shortly. Okay, Calvin cycle, like I said, this is basically like, this is the thing that we're actually after. This is the thing that's building the glucose. It uses the products of the light reaction, so it uses the ATP, because you need energy to squish molecules together. It uses those high energy electrons from the NADPH because we want to incorporate those high energy electrons into the glucose so they can be broken down later to make ATP in respiration. And glucose being a 6-carbon molecule, C6H12O6, we're going to need some carbon. Where do we get carbon from? We get it from carbon dioxide in the atmosphere. Again, ATP is being provided by the light reactions, and it gives the energy needed to squish those molecules together, right? And it also, we need those high energy electrons that also come from the light reactions. It's a good time to remind you of one of those things I said when we were talking about photosynthesis or respiration. I said, in this exam, when you have any questions about carbon dioxide or CO2, when you get any questions about that, the answer is going to be some kind of cycle. So if it's respiration, and we're talking about which cycle produces carbon dioxide, it was the citric acid cycle, right? All those C's to remind you it's carbon. And here in photosynthesis, same thing. Different word, but it's all those C's, right? Which one uses carbon dioxide? Calvin cycle. All those C's should help you remember. Carbon should be a cycle for this exam. Any questions so far? Again, this is just an overview. All right, here's another overview of how it looks. Right, there's the chloroplast that we talked about, that we might talk about. Yeah, we're going to talk about a little bit more later. The light, sunlight energy is hitting it. That energy is being absorbed in these light reactions. We're also getting some water to donate some electrons, which produces oxygen in the process. So since we have these electrons, we excite them with the light. Those are then taken away by that to be used in the Calvin cycle. We also produce some ATP, which is going to be used in the Calvin cycle. That's the Calvin cycle next, right? So the ATP and the high energy electrons go into the Calvin cycle. The Calvin cycle uses those to take the carbon from carbon dioxide and squish them together to make sugar. Now here's something I'm not going to teach you, so I'll go ahead and bring it up now for extra credit. I'm telling you, carbon from the glucose, C6H12O6, the carbon is coming from carbon dioxide. So my question to you, if you want to look it up for independent or extra credit, is where does the oxygen come from and where do the hydrogens come from? C6H12O6. I only told you about the C. What about the H12 and the O6? So for extra credit, you can look that up. Any questions about this overview picture? Okay, you download the PowerPoint. You can watch a little animation that shows this thing in action. So now, again, this is an overview. Let's talk about some other, actually no. This is in the textbook, so I included it, but I'm probably not going to ask you any questions about it. We'll talk about this later in the semester. Later in the semester, it'll be a little bit more important. Technically, there's a term for this. I keep saying that we're using the carbon dioxide in the atmosphere to make glucose. That's called carbon fixation. And again, later in the semester, that'll be important. If you take my 108 class one day, that'll be important. For this exam, I'm only including it because you textbook. Obviously, if plants are using carbon dioxide in the atmosphere to build glucose and other carbon molecules, obviously that's going to reduce CO2 in the atmosphere. which is a good thing right now because we are putting extra carbon dioxide into the atmosphere. Of course, we don't want to get rid of all of it because without carbon dioxide, Earth would be too cold for us because it helps keep us warm. It's just in this case, a little bit too warm. So we screwed around with the thermostat. Obviously, if carbon fixation reduces carbon dioxide in the atmosphere, then the opposite is true. If you cut down trees, for example, then you have less carbon coming out of the atmosphere. All common sense stuff. So does anybody have any questions about this relatively unimportant slide? And I say unimportant in regards to the exam. Okay, so here we go. That was the overview. Now, before we even get into the details of the light reactions in the Calvin cycle, you need a little bit more about how sunlight actually works, right? The physics of sunlight. And you can learn a little bit more about how pigments actually work. Then we'll get into the details of the light reactions in the Calvin cycle. So sunlight is a type of energy called radiation or electromagnetic energy. I'm probably not going to ask you that on the exam. This is to help you understand how it works. So it's the same type of energy when you get an X-ray. I mean, obviously it's not that powerful, but it's the same type of energy. It's the same type of energy used to microwave your food. It's the same type of energy where if you turn your car on, your car radio, and you're getting local radio stations, it's the same kind of energy. But if you can see here, it's kind of in the middle of that spectrum here. Sunlight acts as waves. That's really unimportant for you guys, but it's in the textbook, so I included it. It's actually a little bit complicated. It also acts as particles. But that's a whole physics discussion that we don't need to get into in this class. I'm probably not going to ask you this either, but the distance between two waves, like I said, it acts as a wave. The distance between two crests of the wave, you can see in this picture at the bottom left or bottom right, that's called a wavelength. And the only reason I'm bringing that up is because later I'm going to talk about wavelengths, and then you'll know what I mean when I'm talking about wavelengths. So there's not going to be any questions about wavelength. But anyway, for this whole thing, you start from gamma rays at the highest energy on the left to radio waves, which is the lowest energy on the right. That whole thing is called the electromagnetic spectrum. So mostly, as far as questions are concerned, this slide is not very important. This is more like an introduction, so I can teach you some other stuff later that you'll understand. But you will notice this too, and again, for the exam, this isn't important, that as you go to the right of the spectrum, when you have an increasing wavelength, so the wavelengths are longer and longer and longer, that actually makes it less energy. So obviously the opposite is true. When you go to the left, you go towards the gamma rays, the wavelengths get shorter and shorter and shorter, and that's higher energy. And not that it's that important for the exam, but to help you picture that, imagine if I was holding a rope and Stover was holding a rope, and I was doing this very slowly. Could you picture that like a big old wave if I was doing that really slowly, right? If I did it very quickly, would put more energy in it, then we'd have a lot more smaller waves. Does that make sense? It's the same thing here. Those big, long waves, that's lower energy. But we just put energy into it to get those shorter waves. And if any of you guys know the physics of music, that applies too. Right? When you're talking about lower notes, right? When you get higher and higher, the frequency gets shorter and shorter of those wavelengths. Anyway, any questions so far? All right, this is important for the lab too. When light shines on a pigment, certain wavelengths, i.e. colors, are absorbed and disappear, while others are reflected. So I should have mentioned that too. Let me back up really quickly, sorry. So when we're talking about wavelengths and more energy and less energy, like I said, for the exam, that's not very important. But what is important too, is when we talk about wavelengths, that also changes the color. So you can see, for example, here, the bluish and the purples, that's really high energy. The reds, that's the low energy. Those yellows are kind of in the middle. But yeah, so when you see different colors, what you're looking at is different energy and wavelengths. Now that being said, again, some of it's absorbed, some of it's reflected. So Champion, can everybody see his shirt? See, you can stand up. Do I need to ask him? Can someone tell me which color his shirt is?
Red.
Red, good. Now, why is it red when it comes to this first bullet point? I don't expect anyone to know this. I'm curious to see if anyone can guess. Or some of you might. Why is his shirt red when it comes to the light that's hitting his shirt? That's okay. All right. So it's red because his shirt is absorbing all the colors except red. It's absorbing all the colors, so red is getting bounced back and hitting our eyeballs, and that gets into our brain, and our brain says, oh, that's red. Right? Behind him, Tompkins has got a green shirt. every color is being absorbed by his shirt except green. Green is the one color that's being reflected back to us when it's hitting his shirt. Yeah, so that's going to be important here in the next few slides, and that will be important for lab, especially if you do the last experiment when you're talking about how different colors affect the rate of photosynthesis. So again, his shirt is green because that's the only color it can't reflect. So based on that, what do you guys think the worst color for photosynthesis should be?
Green.
Green, right? Because that's the one color that's being reflected back to our eyes. So if you see a green plant, that's the color, it's absorbing all the other colors. And we're just seeing the green, therefore it's not absorbing the green. So good, keep that in mind. Anyway, this next bullet point is from the old textbook. So I'm only going to go through it very quickly. I'm not going to ask you any questions about it. But the 19th century botanists discovered that only certain wavelengths were used by plants. And that's what I was just getting at right there, right? Green is reflected, so we know, in theory, that's not a good one. All right. Yeah, this is from the old textbook too. I'm going to skip through this. It's another thing I loved about the old textbook. In each chapter, they had like a real experiment that some people had done, like famous people, that was relevant to that chapter. I'm not going to talk about it, but you can download it and read about it. It's good. It gets your brain thinking about these things. But we're not worried about it. I will tell you really quickly though, is this is very similar to one of the experiments that we're going to do in lab next week. It's the one I was just talking about. So you guys are looking, you're going to have different color light bulbs as opposed to shining a whole rainbow. But you're also going to see, which ones photosynthesize more by looking at the change in pH. Here, they kind of did something similar. They had these algae cells, right? They shined a prism on it, right? So you have this rainbow of colors. And then they have these bacteria that thrive off of oxygen, right? So remember, photosynthesis produces oxygen. And they noticed that the bacteria that thrive off of oxygen were hanging out towards here, like the purplish areas, and then again towards there, towards the reddish areas. So that way, that's how those botanists figured out, all right, now we can see what colors are best for photosynthesis, because these are the ones that are producing the most oxygen, because that's where the bacteria are. So again, I'm going to test you on that, but that's a very good, like a slightly different version of what you are going to do in lab next week. Also, remember, one of your questions for the lab and for the lab report are, how else could I test my hypothesis? So, hey, if you did that for your experiment, then there you go. Anyway, if you download the PowerPoint, there's another animation you can watch. We're done talking about the nature of sunlight. Does anybody have any questions about the nature of sunlight? All right, let's talk a little bit more about chloroplast pigments. Barely talk today. Actually, before we do that, well, let's do the next word for attendance. Be Fortnite. I'm not referring to the song from Taylor Swift and Post Malone. It's a video game. It came out on this day in 2017. I've never played it, but I have people in the family who did, so I know all about it. Anyway, so again, pigments selectively absorb lights, right? So again, whatever is reflected, that's the one color it's not being absorbed, right? So whatever you look at, whatever color it is, that's because that's the color that's bouncing off. So the same thing's happening here, right? Green light is poorly absorbed by plants. And that's why it appears green to us, again, because it's reflecting the light. But the rest of that light energy is being absorbed. So then that brings up some stuff we talked about earlier when we talked about the first law of thermodynamics. Right? Energy can't be created, it can't be destroyed. So what's happening to that extra energy? Let's talk about that. Well, first, here's a picture of what I was just saying. Here you have the light. The sun, it appears, usually yellow or orangish, but it's actually white. The only reason it appears yellow or orange, whatever color, is because it's the atmosphere absorbing and reflecting things. But the sunlight is actually white, and it's coming in, and it's hitting. So when I say white, what I mean white light is all the colors. I didn't mention that earlier either, so it's a good time to tell you. If you see a white light, like if I were to turn these lights on, that's all the colors mixed into one. So anyway, you get this white light hitting the chloroplast. All those colors are absorbed. All that energy is absorbed except the green, and that's why it appears green. So we talked about that. We beat that dead horse. Let's move forward. There's 3 types of chlorophyll. I might ask you questions about this. You might need to differentiate between the two, but probably not. But anyway, let's talk about the 3 different types of pigments. chlorophyll A, chlorophyll B, and the carotenoids. Chlorophyll A participates directly in the light reactions. So remember, light reactions is the first of the two stages of photosynthesis. Chlorophyll A is the main player. That's the most important part. It's directly involved in the light reactions. And later, when we talk about the light reactions in greater detail, that's going to come back up. So I'm going to remind you of that one. What I'm not going to ask you for sure is this one right here, the second bullet point. This is just for you to know that I'm not going to ask. Chlorophyll A mainly absorbs blue, violet, and red light. So again, if I ask any questions that differentiate between A, B, and the carotenoids, almost A, B, and C. Anyway, if I do, I'm not going to ask you what color they absorb, but I might ask you their involvement. And for chlorophyll A, that's the big guy, right? It's directly involved. That should be easy to remember because it's A, right? As you might imagine, when I teach you about B, probably yes, it's a little bit less involved. So any questions about chlorophyll A? All right, chlorophyll B. I should flip those. But it conveys absorbed energy to chlorophyll A. So chlorophyll B is like the helping hand for chlorophyll A. Right? I already told you what chlorophyll A absorbs, not that you need to remember it. Chlorophyll B absorbs different colored light, mainly blue and orange. And when it absorbs it, it doesn't use that energy directly. It's like it just gives it to chlorophyll A. It's like, all right, hey, chlorophyll A, I know you're doing the main work here. So here's all the energy I got. And it gives it to chlorophyll A, and then that energy is used directly into the reactions, light reactions. So again, I put a little X through here to remind you. I'm not going to ask you what colors they absorb. Point is, again, chlorophyll B is absorbing different lights than chlorophyll A, so they kind of work as a team. Chlorophyll B gathers that energy, passes it on to chlorophyll A. If that doesn't make sense to you, that's okay, because I'm going to explain it later. Because what do you mean gather the energy and pass it to chlorophyll A? I'll explain later. So any questions about chlorophyll B? All right, carotenoids. They absorb mainly blue-green light. Again, I'm not going to ask you that. Excuse me, blue-green light, not blue and green, right? They're not green, but blue-green light. Carotenoids absorb and dissipate excessive light energy. So the carotenoids are like the sunblock of the leaves, which is interesting to note. Because remember, you think plants need energy for photosynthesis, and they do. They need sunlight for photosynthesis. But there is such a thing as too much of a good thing, right? So too much light will damage the plants, just like it does us. Just like sunlight can mutate your DNA, which we'll talk about later in the semester. It can also mutate the DNA of plants. Therefore, it needs some sunblock, so to speak, and that's what carotenoids are. And I'll talk a little bit more about carotenoids on the next slide. But are there any questions about this? All right, here's some examples of carotenoids. You definitely don't need to know any of this, but this is some stuff you might be familiar with from your everyday life. Beta carotene is a carotenoid. It's a bright orange and red pigment. You find it in pumpkins, sweet potatoes, carrots. Excuse me, right? Things are basically orange things, right? Beta carotene is found in orange things, and it's good for you. That's where you get our vitamin A. Speaking of which, for extra credit, you can look this up. Carrots didn't used to be orange. Humans made carrots orange. So you can find out how, who, why, where, why did that happen? Why are carrots orange? You can look that up for extra credit if you want. Also, you could look up vitamin A. How is vitamin A used in the body? And at the molecular level, what is vitamin A? Right? Is it a carbon-based molecule? Is it a hormone? Is it a cofactor? Is it a coenzyme? You can look those things up. Anyway, that's beta carotene. Lycopene. That's basically bright red stuff. Like tomatoes, watermelon, red peppers. That's lycopene. Now it's very healthy for you. It's an antioxidant. It's being studied for potential anti-cancer properties, amongst other things. I remember there was an article once called Watermelon, Nature's Viagra. That was the Viagra. That was the headline of the article, and it really was about the lycopene in the watermelon being an antioxidant and helping your blood flow and doing what Viagra does. Anyway, again, as far as the exam is concerned, this is a very unimportant slide. But do you have any questions about this? All right, one more thing about carotenoids, and this is timely because we're about to see it ourselves. But when you see the cheese change color, that's what it is. So they're all already there, right? When you look at right now, there's not much of it. It's mostly green. But all that stuff, those oranges and reds, they're already there. We just can't see them because the chlorophyll's, obviously it's chlorophyll. So what happens during the fall, you can look at this up for extra credit if you want to, like what causes it. The chlorophyll leaves, and then we're just left with those pigments. And again, for the exam, not very important. Now, I did say right here that decreasing temperatures cause a decrease in chlorophyll, but there's other stuff too. There's other things that factor into causing the chlorophyll to go away and leaving us with the proteins. Another thing you can look up is why. What's the purpose of that, right? Things don't happen on accident when it comes to natural selection. So why have these plants, not all the plants, but the plants that have done it, how did that evolve? What's the purpose of getting rid of your chlorophyll in the fall and keeping just your carotenoids? But anyway, any questions about that? Okay, again, chlorophyll A, chlorophyll B, and the carotenoids, they absorb different colors. You don't need to know any of this. This is just a good visual reminder of what I was talking about earlier, how all these things act as teammates, right? They all absorb different types of color. So together, like chlorophyll A does a great job with this color. Chlorophyll B and carotenoids do a good job with that color. Carotenoids do a great job with that color, so on and so forth. Again, I'm not going to ask you to memorize any of that, but if I did have a test question about this, I would provide you with this graph and ask questions about it. Say, which wavelength is worst for plants? 550, 650, or 450? And you can just look and say, okay, well, that's about 450. That's about 550. That's about 650. So you say, okay, 550 is the worst for plants. Or I might say, which color does best, or which pigment does best at about 450 wavelengths, or millimeters, nanometers, and you would say, chlorophyll B. Something simple like that. So again, you don't need to memorize any of that, but it is good to be able to decipher a graph. Any questions? All right. Now we're kind of going to get into it. Now that you have this background of the information you need to understand about how light works and how pigments work, now we can talk about how that first stage, how it works. How is it turning chemical or light energy into chemical energy? As I already mentioned, light behaves as waves. The only reason I needed to mention that was to talk about the different wavelengths. And the only reason I needed to mention that was to explain, there's different colors based on the wavelengths. So there you go. But light also behaves as discrete packets of energy called photons. Photons are fixed quantities of light energy. I'm not going to ask you any of this, but I am going to use the word photons a lot. So you need to know what it is so you understand what I'm saying when I say it. And when you get a question that asks about photons or uses the word photons in the question, you'll understand what it is. So when I say photons, I'm talking about light energy. And I will use the word photons a lot, especially in this first section here. As I mentioned earlier, not that I'm going to ask you, but the shorter the wavelength, the higher the energy of that photon. So again, like things like purple and violet, high energy. Things like red, very low energy. Do any of you scuba dive by any chance? Okay. Well, the deeper you go in the water, you start losing colors for this reason. Because the higher, they have different energy lengths. So some of them can penetrate water a little bit better. So eventually, as you get deeper, some of the colors start disappearing and basically turn into gray. But anyway, at least natural light. Now, if you're down there with a flashlight, that's a different story. So any questions about this relatively unimportant slide as far as the exam is concerned? Okay, a lot of this is going to be a reminder. Some of it's going to be new. When a pigment molecule absorbs a photon, well, no, this is all new. All right, so before I even say this, I'll remind you. Like we said, champion shirt is red. The reason it's red is because it's absorbing all the colors except red. Red's being reflected back to our eyeballs. That's why it looks red to us. Now, the opposite is true, not the opposite. But think about a black shirt. A black shirt is absorbing all the colors. It's not reflecting anything back. That's why it looks black to us. That's why when you go out on a hot day or a sunny day, your black shirt will warm, it'll make you warm. Hot sometimes, depending on the situation. And you may not know how that works, but now you're going to find out how that works. So what's happening, not just with a black shirt, but with any time of a pigment absorbs that light energy, what happens is, there's electrons, right? Because we're dealing with molecules here, molecules and atoms. light energy hits these molecules, the electrons get excited. I don't even have this would be a whole semester to try to explain thoroughly what I mean by excited, but just know it's high energy. Excited just means high energy, right? So again, those electrons are absorbing that energy from the sun. They become highly energetic. They become excited. It's a very unstable state, so they can't stay that way long. So then they lose that energy. They kind of fall back down to where they started. But as you know from the first law of thermodynamics, energy can't be created or destroyed. So when it's losing its energy, that energy has to go somewhere. Going back to what I was talking about being hot on a summer day with a black shirt, in that case, you know, those pigments are absorbing the heat or the sunlight energy. Then you release that energy, and in that case, that the energy is lost as heat. Because remember, every time you convert energy from one form to another, you know, you lose some as heat. But in that case, almost all of it is being converted to heat. And that's how it works, right? Again, the electrons get excited, they can't stay that way. They lose that excitement, that energy is released as heat. But obviously, that's probably not what's happening with photosynthesis, right? We know that in plants, they're using that energy to make ATP and then ADPH, or high energy electrons. I already told you that. So it's just reminding you again. So any questions about this slide? Okay, I'm probably not going to ask you questions about the photons exciting the electrons and then the electrons losing that excitement and releasing the energy. I'm only explaining this so you know how it works. Here's the visualization of what I'm talking about. Here you have a chlorophyll molecule, light hits it, the electrons in that molecule get excited, right? And then they lose their excitement, and as they're losing that excitement, some of that is released as heat. Sometimes it's released as light, but not always. That's just an example of sometimes what happens. So I'm going to put an X through that, because not all the time does that happen. This is from the old textbook. I don't think the new textbook mentions this, which is, in my opinion, a good thing, because we don't really care about what fluorescence. We're not worried about fluorescence. But I kept it in. Same with this slide too. This is really unimportant as far as the exam is concerned. So again, when these pigments get excited, the electrons in the pigments get excited, they lose that excitement, they release this energy. Sometimes they do admit it as light. And again, this is from the old textbook, but I decided to keep it anyway, just for your own trivial knowledge. It's very unimportant as far as the whole semester is concerned. If you've ever used a glow stick, and this is completely different, I don't know why your textbook included this, but the old textbook, but that's not due to light's energy. This is due to when you break it, you know, I'm sure you've used one of those before, right? You crack it. What happens when you crack it is those electrons, or those two chemicals mix. What's happening there is then you're having a chemical reaction that is exciting electrons, and in that case, the electrons then lose their excitement, and they're releasing that energy as light energy. So that's the only reason that's even relevant to what we're talking about, right? Is this idea of electrons get excited, and then when they lose that excitement, they release energy. And in this case, they got excited because of the chemical reaction, and the energy they released was in the form of light. But specifically, that specific example doesn't matter for us. But the idea here is, again, electrons get excited, they release that excitement, they release heat, or release energy. All right, so here's a term I told you about before, and I said you need to know what it is just because I'm going to use it again, so I'm using it again. Inside the thylakoid membrane, which is a part of the chloroplast, right? The chlorophyll molecules are organized with other molecules into something called photosystems. And I'm probably not going to ask you about photosystems either. But again, this is a term you need to know because I'm going to use this term when I'm teaching you other things. And in the exam, I'm going to use that term. And I'm not going to use it like, what is a photosystem? But I'll be describing a scenario, and I'll use the word photosystem and ask a question about that scenario. So if you don't know what photosystems are, you don't know what the scenario is, therefore you won't know the answer to the question. So what is a photosystem? Each photosystem has a cluster of a few hundred pigment molecules. So basically, a photosystem, as far as we're concerned, it's just a bunch of pigments organized together. Here's a picture of one. So here's the thylakoid membrane. All right, here's the whole chloroplast, right? We've got all these thylakoids. Now we've zoomed into this one part of the thylakoid membrane, and look at that. That should look familiar to you. It's a phospholipid bilayer, just like our cell membrane. And embedded within